Welcome to this lecture series in complex numbers. We are looking at a very nice problem. So fix a positive integer n. Show that this sum, which I will explain in a little bit, this sum is equal to this peculiar expression. So what is this sum? I'm sure you know this symbol n choose r. So n choose r means n factorial divided by r factorial times n minus r factorial. Actually, it doesn't mean that. It means the number of ways of choosing r objects out of n objects. That's what it means. It turns out to be this. So the problem is to compute n choose 0 plus n choose 3 plus n choose 6 and so on, meaning these things at the bottom that appear, they are all multiples of 3 and they are all non-negative and they are all at most n, of course. So that's what this sum is, and we want to show that it is equal to this thing. And yeah, you can experiment and see that this actually works, and I find that extremely pleasing. Why would a cosine of anything appear here? But it's not as mysterious as it would seem, at least not in this case. And a more formal expression of the above problem is this. So instead of writing this thing, we can write this. This is a more formal way to express the same thing. As usual, one is encouraged to pause the video and try to solve it oneself before going forward. And now let us move on to the solution. And before we do that, we have some notations and a few remarks to make. So let omega be this particular complex number, which is nothing but a certain third root of unity. So if this is the unit circle, then there are three roots: omega, omega square, and 1. So this guy is what we have written here. It's the this angle is 120 degrees, 2 pi by 3 radians. All right, so 1 omega and omega square are all the three roots of unity, and if you fix a positive integer k, then there is this very simple exercise. Show that this quantity is 3 if 3 divides k and 0 otherwise. You can check that. So suppose this k were equal to 1, so 3 does not divide k, and what is 1 plus omega square? It is obviously 0. And if k were equal to, let's say, 3, then 1 plus omega to the 3 is 1, and omega to the 6 is also 1, and therefore this is indeed 3. And this is easy to verify in general. All right, here is some theorem that we are going to use. It's called the binomial theorem. So this is a polynomial expression, 1 plus x times 1 plus x times 1 plus x n times. That turns out to be this quantity, which can be written in this way. So n choose 0 plus n choose 1 times x plus n choose 2 times x squared, and so on. So if this is not familiar to you, you can Google and see a proof or come up with your own proof or just accept it. Any of those things are fine. And now let us go to the solution that will solve our problem. So we have 1 plus x to the n is this thing, as we just mentioned. So what we will do is we will substitute x equals 1. If we do that, we will get this. Right. If we substitute omega, we get this. And we just discussed what we mean by omega, so I'm not repeating that. And let us also substitute omega squared. So we will get this. And now let us add all the three things. So on the left hand side, we will get, this is nothing but 2, so I will write that as 2 to the n plus 1 plus omega to the n plus 1 plus omega squared to the n equals summation k equals 0 to n choose k 1 plus omega to the k omega to the 2k. All right, and we discussed that this is equal to 3 only when k is divisible by 3, and otherwise this is 0. So the right hand side expression is n choose 0 plus n choose 3. Sorry, it's not n choose 0, n choose 3. It is 3 times n choose 0, n choose 3, n choose 6, and so on. and on the left hand side. So we have achieved what we wanted to achieve on the right hand side. The rest of the problem just works itself out, but let's do it in full. So what is 1 plus omega? 1 plus omega is cis pi by 3. You can compute it explicitly and see that that's correct, but I would encourage you to see it geometrically. All that's happening is we have, this is omega, this is 1. So if you add 1 and omega, you are going to get this guy, which is at 60-degree angle. And you can see it in various ways. If you translate it, it forms an equilateral triangle here and so on. But whatever, you can just compute 1 plus omega. Since you know what omega is, you can just compute 1 plus omega and agree with this equality. And similarly, 1 plus omega squared is, so what it should be, it is just the the conjugate of the previous one. So just to verify this, so let me write that as cis pi by 3 bar. All right. So on the left hand side of this equation, meaning this part, that becomes 2 to the n plus cis pi by 3 to the power n plus cis pi by 3 bar to the power n. That is equal to what we just said. All right. But now we use what is called de Moivre's theorem. So that is cis n pi by 3 plus cis n pi by 3 bar. That is equal to 3 times the required quantity. Right, and what is this? This is 2 cos n pi by 3. And that is 3 times, that is the right hand side. Copy, paste. Wonderful. And I think this matches with what we wanted. So what we wanted to show is 1/3 of that thing is the required quantity, and we have 3 times the required quantity is that thing. So if you just divide by 3, you get the correct thing. So that's all. The main idea is to, kind of kill off the exponents which are not divisible by 3 by substituting these 2 cube roots of unity. So that's that. And by the same logic, if suppose one was asked to compute something like, let's say, this. Something like this, you could do the same thing. Instead of omega, you would be substituting all the 5th roots of unity. And it wouldn't be as nice as what we get here, but you can still compute it explicitly. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.